This video will talk about plate tectonics and how the plates are moving at different plate boundaries. We're going to start our lesson today by talking about lithospheric plates and discussing how they move. And in order to discuss lithospheric plates, we have to talk about the two types of crust. Please make sure that you have page 10 and page 5 of your reference table handy, as we will be looking at both throughout this section. To start, let's review what lithosphere is. Lithosphere, if you remember from your reference table on page 10, is the crust and the rigid mantle. This broken piece of crust that you see at the top is going to represent our lithosphere. The center of this is the center of the Earth, which we know is our hot inner and outer core. Underneath the lithosphere, you should already know that there is the asthenosphere, or the plastic mantle, which has our convection currents in it. Remember, convection currents are what move the plates around. So what will happen is your warm magma will rise. As it gets closer to the crust, temperature decreases. And that cooler magma will sink back down towards the core, while it will warm up again and rise to the crust. Now, what we're concerned about is what's happening as you reach the crust. Well, in this area, you will see that the two plates are being pulled apart by the magma cooling, which would be a divergent boundary. But over here, if we complete the convection, we would see that right in this location, we would have a convergent boundary. So all around our planet, we have strategic divergent and convergent boundaries due to the direction the plates are moving and, of course, how those convection currents are moving underneath the Earth's surface. Remember our two types of crust. We have continental crust and oceanic crust. Oceanic crust is thin, continental crust is thicker. And if we look at our reference table, we can tell the difference in densities and the composition. So continental crust is made of granite with a density of 2.7. Oceanic crust is made of basalt with a density of 3.0. Again, make sure you know most of this stuff you can find on page 10 of your reference table. And this is the basic information we're going to need today when we talk about divergent, convergent, and transform plate boundaries. Now that we know what is moving the plates around, we have to figure out what's happening when two plates bump into each other at a plate boundary. This section will talk about two different divergent boundaries, a divergent boundary between two pieces of oceanic crust and a divergent boundary between two pieces of continental crust. Let's first start with the oceanic crust. Since it's divergent, remember we have to draw in what actually is causing that divergence, which is convection in the mantle. So we have hot magma rising up, and then as it cools down near the crust, it's going to pull apart and pull that crust with it. So we want to draw crust direction pulling apart at the center. Now you might remember this from our activity the other day. As this crust pulls apart, this hot magma will be able to seep out onto the oceanic floor, creating young, new crust. And as we move out away from this area, you're going to see older crust forming on either side. There is a little bit of height pushed up here in our crust due to the magma being pushed up, so this is known as a ridge. A really great example of this is the Mid-Atlantic Ridge. And if we look at page 5 of our reference table, the Mid-Atlantic Ridge runs right down through the center of the Atlantic Ocean. And you'll notice by looking at the key at the bottom, this is a divergent plate boundary. So you can see that the oceanic crust is being split apart by the convection current. So we want to make a little bit of a note down here. We want to say that we will have new lithosphere created. And that would be in the center of this ridge. We want to say that the convection current is going to lift the crust to make a high place, which is your ridge. And we also are going to find that some effects we could have here are very shallow earthquakes. And throughout this, I'm going to abbreviate earthquakes as EQs. Okay, so we're going to have really shallow earthquakes happening here because anytime you have plate movement, you have a shifting or breaking in your rock, which could result in an earthquake. Continental divergence is similar, except that we're not going to see the magma pushing through the crust. Because if you remember from what we just discussed, oceanic crust is a lot thinner than continental crust. So we do want to draw our convection, rising up and then pulling those plates apart. So we do have the divergence happening here. But now since this continental crust is pretty thick, we're going to see that the magma can't make it through and it's not going to separate all the way. So what actually is going to happen is we will start to get these breaks in the rock, which we call faults. So you'd be able to see this on the surface, and we can actually call this whole entire feature right here a rift valley. So a great example of this is the East Africa Rift Valley. Now over a long period of time, what can happen here is that you can start to get water form, and this could develop a lake or even a sea. And actually, the Red Sea was formed in this way, okay, due to this divergent boundary between continental crust. So our effects here are going to be, of course, earthquakes. Anytime you have plates moving around, you can eventually have earthquakes. A rift valley, which is this feature right here. Maybe a sea or a lake forming if water gets filling up in that area. And then the faults, because the rock is moving apart. Remember, new lithosphere is not being created here. Instead, it's just breaking itself down and splitting apart.